Guys, those who are online, are you able to hear me?
Yes, sir.
Okay. So did I show you that activity that paramagnetic substance? I showed you a video, right?
Yes.
So did I explain about hysteresis loss or hysteresis effect? Something like that? No, right? Yeah. So this, I've showed this graph, right? I mean, the box from which where I discussed the concepts. So now you remember what is a paramagnetic, diamagnetic, and a ferromagnetic substance, right? Can you tell me what exactly they are? So what is the difference between paramagnetic and ferromagnetic substance? What about paramagnetic? Yes. So paramagnetic and ferromagnetic substances both attract the magnetic materials, except the fact that ferromagnetic is way stronger compared to paramagnetic substances. Just a minute, I'll close the door. Yes. So now we'll discuss about the next important concept, which is called as hysteresis loop. Okay. So write down the heading as hysteresis.
Sir, can you repeat the D?
I've written it, see, copy it. Hysteresis loop. Okay. So what does this mean? Okay. Now, I would have given you certain definitions for magnetic substances, out of which one of the definitions would have been mu is equal to B divided by H. Please revisit. So mu is written as B divided by H, where mu is what? Mu is the permeability of the magnetic material. B stands for magnetic induction. It's not magnetic field, it is magnetic induction. And what does H stand for? It's the magnetizing field intensity. So magnetic induction is basically the output, and magnetizing field intensity you can take it as input. So B divided by H, correct? So from this, what can I say B will be equal to? So mu times H, is that clear? So I'm trying to say that the magnetic induction is equal to mu times the magnetizing field intensity. Suppose I take B to be on the y-axis and H to be on the x-axis. This is of which form? Y is equal to m into x. Is that clear? So it is of the form Y is equal to mx. So if you revisit mathematics and try to recollect what shape that particular graph represents, Y is equal to mx is basically what? It is a straight line that passes through the origin. Okay. Now what we are going to do is, see, listen to this carefully. Okay. We are basically plotting a graph between B and H, where B is taken on the, where output is taken on the y-axis and the input is taken on the x-axis. Is this point here? Now, this graph mainly speaks about how does a ferromagnetic substance behave when it is placed in the presence of external magnetic field. Means if I have a ferromagnetic substance, right? If I have a ferromagnetic substance and I take and place it in the external magnetic field that is present, then what would happen to this ferromagnetic substance? It will get magnetized. So the material will get magnetized. Is that right? Are you able to understand what I'm trying to say? So when this is getting magnetized, now the question is, how fast or how slow is it going to respond to the input value, that is a magnetizing field? Means as soon as you take a ferromagnetic substance and place it in the presence of external magnetic field, is it going to immediately acquire magnetism, or is it going to acquire magnetism slowly, or will it be in proportion? Means as you keep increasing the value of it, will the magnetic induction also increase in proportion? That's what we are going to answer. For that, we will take the help of this expression B is equal to mu into H. So Y is equal to M into X. So what does this equation tell us? It tells us that the magnetic induction is directly proportional to magnetizing field intensity. Means as you keep increasing the magnetizing field intensity from 0 to 1, magnetic induction should also increase from 0 to 1 in proportion, or it can be 0 to 2, something like that, depending on what is the value of M. Okay, but with increase of X here, but increase of X in the value of H, there will be an increase of mx value in the Y. That is the meaning of it. So when you increase, for example, let's take this. Let's say the magnetic induction has got increased from 0 to 1. Sorry, magnetizing field intensity has got changed from 0 to 1. Then let us say B is changing from 0 to 3. Suppose you change the value of H from 1 to 2, what should happen to B? It should change from 3 to 6. What happened? Okay. So it will change from 3 to 6. Suppose if you change the value of H from 2 to 3, what should the value of B change from? It should change from 6 to 9. So you're able to understand the meaning of proportion. So for every value of change here, for unit value of change here, what is the corresponding proportional value changing in H? That's what the equation tells us. B is equal to mu H. So if that is the case, then for a ferromagnetic substance, if I'm asked to plot a graph for this, then what am I supposed to do? I should have plotted a graph as a straight line. Is that right? Am I clear with this? But unfortunately, This will not work. Because what is the nature of ferromagnetic substance? Ferromagnetic substance has a very high susceptibility. What is the meaning of susceptibility? Means it can get affected fast. Means even for a lesser value of magnetizing field that you apply, there will be a more value of magnetic induction that will take place. So the graph will no more be a straight line, rather it be a curve such that the curve will be inclined more towards the y-axis. Means as you keep, listen to this carefully, okay, as you keep increasing the value of H, the magnetic induction will not increase linearly, rather it will go in a curved path, and there will be a particular value at which it will get saturated. So what is the meaning of saturation? Beyond which, whatever is the input you are going to give, the output will be fixed. It is not going to respond anymore. Means that material cannot take any magnetic induction beyond that point. Is that clear? Right. Now the next question. I will increase. I understood that the saturation condition is achieved. Now what I will do is I will immediately remove the magnetizing field. What are we doing? We are removing the magnetizing field. Then what is our expectation? So when you remove the magnetizing field, what is that we expect? We expect this ferromagnetic substance to lose magnetism instantly. But will that happen? If it happens, then it is no more a ferromagnetic substance. So it is not going to lose instantly. Rather, what will happen is the path will be, so when you remove the value of H, the path will be in such a way that it will come back in this way. Okay. So initially, try to observe from O to A. When you keep increasing the value of H, the graph follows the curve O to A. Okay. As soon as you remove the magnetizing field, that is, as soon as H is made 0, what will happen is it will start retracing the path. So what is happening? If you observe, the graph is coming down. So down in the sense, it is losing its magnetic induction. But the question is, when the value of H is 0, is the magnetic induction also 0? No, right? Then this value, I will call it as P prime, for example, or B dash. Then this OB dash is what is called as retentivity of this material. It's called retentivity of this ferromagnetism. So is there any confusion to this point? What happens is value of H beyond what? Again, if you increase again, you get magnetized. It will not get, it will go from here to slightly above. Above, but it will attain the saturation value. Actually speaking, it should go in this further. Because there is a saturation value associated. It will not become high. It has a limit beyond which it can't take. Okay. This is point clear. Now what will happen is, observe at B dash, magnetic induction is not equal to 0, whereas H is equal to 0. Is the point clear? So what will happen? Magnetic induction is not equal to 0, but H is 0. Then the distance OB dash is called as the retentivity of the ferromagnetic substance. Means it is the value of magnetic field it is able to hold within itself. Now next point is, we have made the magnetic induction 0. Now you are again making the magnetic induction a non-zero value, but in the reverse direction. In the sense, you start applying the magnetic induction here, but the change here is when you applied in the positive direction, initially the magnetic induction was also zero. Magnetizing field intensity was also zero. That is why the graph started from zero. Whereas in this case, the graph is not starting from 0, 0, rather it is starting from 0, b dash. Means the material is already having some magnetism associated with it. Now, by applying the value of H in the reverse direction, what are we trying to say? Means you have reversed the direction of magnetizing field. Now listen to this carefully. Okay. If this is the magnetic substance, okay, if this is a magnetic substance, if this is the direction of field, then inside the ferromagnetic substance, magnetic induction will also get induced in the same direction. Okay, listen to this. H and B will be in the same direction. Now, what did you do? Initially, there is a B generated inside this material. Remember, it's a non-zero value because it is having some retention. Now, if you reverse the direction of H dash, what will that H dash try to do to this B? It will try to cancel it out. So it should cancel it out, and there will be a particular point where the magnetizing field intensity will not be zero, but magnetic induction will become zero. Means the graph, when it continues in this path, it comes and hits here. So at this point, what is happening? This is some value, I call it as H dash, okay, where B is becoming zero. What is the meaning of this? Means the reverse magnetizing field has actually removed the magnetic property of the ferromagnetic substance. Are you able to understand what I'm trying to say? So it's a slightly complicated concept. You need to pay attention. If anything is not clear, please ask. So when you have applied the reverse magnetizing field, you actually demagnetize the material. That is why it came to the point C. Is that point clear? After this, what you will do is you will keep increasing the value of H in the reverse direction. It is not negative H. H in the reverse direction. Then what will happen is the graph will go in the downward direction, right? And it will attain a saturation value here. Is that clear? Now again, what you will do is you will remove H dash again. Sorry, you will remove the reverse value of magnetizing field again. Now what will happen? Again, the material will start getting demagnetized. It will start losing its property. So it will follow a reverse path and it will come and hit the y-axis here. Then what is this distance called as? Then what is this distance called as? If this is C, if they call this as D, then what do I call OE as? I've already discussed this thing. That is also called as retentivity. Why? Because the material is able to hold some magnetism within itself. Okay. Now again, what you will do is from here, you will start increasing the value of H in the positive direction. Means the whole game is the magnetizing material is kept in the same direction, but you are reversing the direction of magnetizing field. By doing it, you will be getting this kind of a loop. Again, when you start increasing it, you ask me, what will happen? Now the graph will again go in this path and it will meet at this point only. It will form a loop, not like it will get shifted every time. So what does that indicate? Means in whichever direction you are trying to apply more amount of magnetizing field, the magnetic induction is always a fixed value. Because that ferromagnetic substance will have a limitation associated with it. It is like you have a 1 liter bottle where you can't fill 2 liters of water on the mass. So it has a saturation, right? Same logic. You're able to understand? So this is what happens. And this loop is called as hysteresis loop. Okay.
If we apply reverse magnetism
Which the graph will start in this direction. Means this graph would exactly be a mirror image with respect to origin. Almost yes. They'll be this. we need to understand two important terms from this graph. One is called retentivity. So if you observe the graph, right, retentivity is a point where h is 0, but b is not equal to 0. There is a point C, right? At point C, what is happening? B is 0, but h is a non-zero value. So what do you call that OC as? That OC is called as COERCIVITY. It's called coercivity. Coercivity. The meaning of it is something is coerced. How much is the reverse value of magnetizing field that we need to apply? Because that is corresponding to x-axis. OC corresponds to x-axis. So x-axis who's there? Magnetizing field. So the reverse amount of magnetizing field that you need to apply to make sure that the ferromagnetic substance is completely demagnetized. So the reverse value of I'll give you the definition first. Listen to this and understand the concept. Okay. Reverse value of magnetizing field that we need to apply so that the material loses its magnetic property. Means it should become a completely demagnetized material. So coercivity is related to the amount of reverse field that you apply. That is input. Retentivity relates to what? It is the amount of magnetism it is able to hold. That is related to output. Are you able to understand? So whenever you analyze any graph, right, you need to ensure one thing, which is lying on the y-axis and which is on the x-axis. Based on that only you will understand it. Am I clear to this point? Right? Did you all draw this graph? Yes? ADP, because that is the maximum value of reverse field, right, that you're applying. It is only for ferromagnetic. It is only because diamagnetic and paramagnetic substance do not have retentivity limit. Now I'll tell you one point. In the last class, I have shown you this table, right? In this table, I've explained it. Since you asked this question for 11th point, hysteresis effect clear. First one is diamagnetic. Second one is paramagnetic. Third one is ferromagnetic. So what does a diamagnetic substance say? B shows no hysteresis. What about a paramagnetic? No hysteresis. So hysteresis is applicable only for a ferromagnetic substance. If you see, hysteresis is a very complicated name. If you see the basic meaning of it, it means lagging. One is lagging behind the other. So the simplest meaning of hysteresis is lagging, lagging. Okay. Now, can we see the definition of retentivity and coercivity? Write it down. What is coercivity? I told you about it. It is the, if you read the definition, you will understand it. It is the intensity of applied magnetic field which is required to reduce the magnetization, means to completely demagnetize the material. To reduce the magnetization of a given magnetic material to zero. Okay. In other words, to coerce the material to surrender its magnetism. Coerce means you are applying the reverse value of something. You are forcing something to lose. So write down this definition. It is the intensity of applied magnetic field required to reduce the magnetization of the given material to zero. In other words, to coerce a material this means to surrender the magnetism. So what is retentivity? Retentivity, so name suggests no retaining something. It is the capacity of an object to retain magnetism after what? After the action of magnetizing force has been ceased. Is it clear till this point? So from this I have a question. If you want to design a permanent magnet, right? What kind of a ferromagnetic substance will you choose? If you want to design a permanent magnet, what kind of a ferromagnetic substance will you choose? That material should have high retentivity and high coercivity also. Retentivity and coercivity, if they both are high, then that material will be used for a permanent magnet. Whereas you want a material to lose its magnetism fast, then you use something called as a soft iron material, which is also a ferromagnetic substance. If you see the word iron, it is ferromagnetic. That's it. Am I clear with that point? So remember this word soft iron, you'll be learning about this in the 7th chapter under the device called transformers. So there also you have something called as hysteresis loss. So you need to have an understanding of this. Clear? Right. And the last part of this chapter is Earth's magnetism. So we have completed two major parts. One is about permanent magnets like bar magnet, right? And we saw how a bar magnet and solenoid are similar. We saw the two derivations, right? Right. Apart from that, you have this thing about the magnetic properties of the material. That also we have completed. Now the last part that is left out is theory of Earth's magnetism. Okay, we'll see that. Shall we get started? Okay. So you know a device named compass, right? What does it do? Why do we use a compass in the first place? For navigation, right? For navigation, you need to know which direction is, which is the direction in which you are trying to move. Is that right? So for you to find the direction, you have a compass which is made up of magnetic needle, right? Where is that compass placed in general? So what you generally do, you take a compass and place it in your hand. Then what will happen to the needle of the compass? It starts deflecting, right? Now recollect the concept that when a magnetic material is placed, when a magnetic dipole is placed in an external magnetic field, what will happen to it? It will start experiencing torque. So due to the torque, it is revolving. Is that right? Right. So that is the reason why a compass needle is revolving. But the question is, you're holding it here. Till now, we know the fact that Earth has only gravitational field around it, right? But I contradicted a statement here. Compass needle is made of, it's a small magnet. Then how is a magnet able to respond to gravitational field? Then there is something that we need to observe. What is that we are able to observe? That there is magnetism exhibited by Earth also. Apart from the gravitational field that it exhibits, it has some amount of magnetic field also exhibited by it, which is a very, very, very small value. It is in terms of few gauss. That's not the story here, but it exhibits. If at all it is able to exhibit, then what are all the parameters I need to keep in my mind so that I am able to do a proper navigation? Means when I take a compass and exactly place it in the presence of magnetic field, is it exactly showing me the right direction? Or is there some error that is occurring due to which I need to know what values to be corrected for me to go in a particular direction? So these are all the questions we need to ask. For that, you have something called as elements of Earth's magnetism. Okay, we'll be discussing about two things here. One is, why is Earth's magnetism even existing in the first place? That is, why is Earth exhibiting magnetism? Secondly, we will try to understand what are all the elements that are associated with respect to this kind of Earth's magnetism. But I told you the value is very less. That is a permanent magnet. The magnets say, oh, when they design a compass, right, there is a weight of the needle also taken into consideration. consideration. They will not take a big rod and keep it there and ask you to rotate it. So they will keep it in such a way that it is able to respond to the Earth's magnetism at that point. So the values will be calculated previously. So based on that only design takes place. Whereas when you talk about a current carrying conductor, if that is the case, like how you are asking, if I take an iron object and place it here, it should get attracted. Why is it not happening? Even if I remove the insulation, for your information, even if I remove the insulation, I pass this current, right, the effect will be very small. So that is why we are trying to calculate the values to understand how much value is being created. So whenever you are studying science, right, there are 2 points you need to understand. One is an effect is happening. Yes, it is happening. Second is how effective the effect is. How effective in the sense, how powerful that effect is to create an impact in the surrounding parameters. So just because we learned that every current carrying conductor should exhibit magnetism, then everything should get attracted. I also told you an important point that even we exhibit magnetism because we are also made up of atoms only, and atoms have electrons which are involved. But why are we not able to do it? There are certain parameters that are associated. The strength, maybe we are doing it, but the sense is not sufficient enough for you to feel it. Same is the case here also. Yeah. But here comes the tricky part. So if you ask the reason for if you ask what is the exact reason behind Earth's magnetism, nobody knows. There are only different theories that are proposed, and there are some theories also stating that the direction of poles of the Earth's magnet will also change after a few years. That's what the theory says. Okay. Now see. So if you see the first point that says the first point itself starts like this. There is no concrete reason for the cause of Earth's magnetism, but there are few theories. 11th is it? Okay. So one of the theories that is used to explain Earth's magnetism is called as dynamo effect. So what it states is, see, I told you one point. Wherever you see magnetism, right, what is needed? For magnetism to be exhibited, what is the preliminary thing that is supposed to happen? Charged particles should be in motion. So they can be in any form. Charged particles are needed, they should be in motion. It is not necessary that only electrons are there. You can have any charged particle and put the charged particle in motion. Around it, you will have magnetism. So having that theory in mind, what they told is the outer core of the Earth is there. So when you divide the Earth into different layers, if you take the outer core of the Earth, then they're saying that the Earth has molten form of the iron in the molten form, right? And other heavy elements in the liquid form. Okay. So the inner core, what it does is it solidifies under the influence of gravity. I told you, right? You have Earth's magnetism as well as gravitational field. So due to the rotation of Earth and gravitational field, what happens? The materials which are present in their core are solidified. If they are solidified, what is going to happen? They cannot obviously flow, right? So what they are trying to say is there are metallic particles, right, which are in the fluid state. At which part? In the outer core of the Earth. Now they are saying that these molten particles motion in the outer core of the Earth is one of the reasons why Earth's magnetism is existing. That is one of the theories proposed. Second, there is something called as ionization of outer layers. Okay. So what happens is this theory tells us that the rotation of the Earth about its own axis. So Earth is revolving about its own axis. It will produce strong electric field due to the ionization of outer layers of Earth. Means what will happen is when the Earth itself is revolving, there are some particles which are in contact with Earth, right? So due to friction, what can happen is those materials will get ionized. In the sense, they get charge associated, right? So when charge is going to come, they are saying that this produces magnetism. Due to whom? Due to the movement of ions that are taking place. However, if you take the theory, right, according to the theory, if you see, dynamo effect is more acceptable theory. It is acceptable theory, but it is not 100% true theory. Is that clear? Okay. Now, having said this, we need to understand how the Earth's magnetism is actually going to exist.
Sir,
Yeah, tell me.
sir, can you tell dynamo effect once again?
Dynamo effect on the outer core of the Earth has molten iron. Okay, inner core has solids. So the molten iron and the heavy elements which are present in the liquid form actually flow. So when they flow, what can you say? They constitute electric current, and due to this electric current, they are saying magnetic field is generated. Yes.
Okay.
So if you take Earth, right, and wash your face. So if you take Earth, right, you have four important terms that you need to have. Okay. So for Earth, you have North Pole and South Pole. You know about this, right? So you have the geographic North and the geographic South. Similarly, you have something called as magnetic North and magnetic South because of magnetic properties. Are you able to understand this? So if you take this to be the, one minute, I'll use another color. Okay. If you take this to be the North Pole, okay. If you take this to be the geographic North, and if you take the bottom to be the geographic South, okay, which I'm writing it as NG and SG. The subscript G stands for geography. Okay. If these two are the North Pole and the South Pole, according to the geography, you can observe an important point that when you try to take the compass and draw the magnetic field lines, okay, when you try to take the compass and draw the magnetic field lines, we can observe that the geographic North Pole coincides with the magnetic South. What happens? It coincides with the magnetic South, and the geographic South will coincide with the magnetic North. That is why if you see the magnetic field lines, generally what is the direction of magnetic field lines? They start from the North Pole and go towards the South Pole, and inside they are from the South Pole to the North Pole. So that is why if you see the direction of magnetic field is from the geographic South to the geographic North, means magnetic North to magnetic South. So this is one important point that you need to have in your mind. That is how it works. Yeah. They will send some satellite and check out what is our position. They will send some satellite and check it. What is the some satellite or something will go and take an image and send it. You take an image from some far distance and send it. Okay. Earth looks like a. See that it is made of many materials that you have to get to the geographical part and the chemical part only. If you want, I can check and tell you. That is one of the forms because of the heat. When can something exist in the molten form? When there is a lot of, so it is because of the heat the iron is existing in the molten form. That is what is happening. But if you want me to find out the other materials and tell you, I can check and tell you. You can give me some time. Okay, if you're interested to know about it, even I'll find it out and later. See, that is one of the components. I'm not saying it is completely made of. That is why they told other heavy elements also present. But I'm interested to know. I'll try to find out and tell you. We found out. I don't know. It's a theory proposed. I don't know the exact reason for every theory that is being formed. Certain things I read and tell you. Certain I have a logic to it. This I don't know. Maybe if I can find out and tell you, I'll make it. It is actually a magnet. Yeah. Yeah. Yes. With south. Geographic south and magnetic. That is actually facing towards the geographic north. Yes. pointing towards the geographic north. Because the compass job is to exactly show us the geographic values, not the magnetic values. Okay. So that is why geographic north is also sometimes referred to as true north. You asked me clearly, right, why is this happening? So even before this, what people thought is, so even before the theory of compass and other things were existing, they thought that the geographic north and the magnetic north were the same. So at that point, they thought about it. Okay. Then what happened after the invention of compass and other things? We could sense that it is actually the reverse of what you had thought. That happens. That is why I told you, the direction of magnetic field will also keep reversing after a few years. That happens. It is all because of the rotation of Earth. If you get into too much of details, there is no point. Yeah, I have to do a research and commentation. I tried studying about it because when you go for hiking and all those things, right? When you have a compass in your hand, there are certain things where there will be errors that will be shown. So those errors are happening because the value of magnetic field at every point is not the same. So due to which there will be a small deflection that will occur. That is what we are about to study about the Earth's magnet, the elements of Earth's magnetism. Okay. I'm not saying wrong direction completely. There will be a small variation that will occur. Okay. It will deflect in a different direction to the geographic north. Okay, thanks. Sorry, I didn't get your question. The deflection is the needle points towards the geographic north. In the presence of external magnetism. Okay. So it will point in a different direction. Okay, you're saying, okay, let me process your question. You're saying let's assume that there is no Earth's magnetism at all. You place the compass. Is that what you're saying? Other than? Okay. So you're saying some other external magnet? Yes, it will get disturbed. Yes. Yes. It can happen. It can be because of your mobile phone also. It can happen. But initially the Google Maps and all those things, they work like that only. That's like you see, there will be an approximation shown to you. When you're sending a message in WhatsApp, right, when you're sharing the right location, it says 65-meter accuracy. Like somewhere surrounding. So there will be a slight amount of error because those are all found using the triangulation technique and all those things. Okay, but the whole logic is about using the Earth's magnetism. Okay. So is that clear? So I was telling about 2 points. One is called the geographic north and the geographic south. Similarly, you have magnetic north and magnetic south. Is that clear? So for all, you are able to define an imaginary line through the geographic north and the geographic south. You call it as geographic axis. What do you call it as? So you call it, you have an imaginary line which passes through whom? The geographic north and the geographic south. Okay. Then this line is called as the geographic axis. Okay. Now the next point is, if you are able to define a plane, that is a two-dimensional shape which is perpendicular to the axis of it, which is perpendicular to the axis of which is perpendicular to the geographic axis, you call it as geographic meridian. So are you able to understand? Harish, door close. So did you understand what are the difference? One is one-dimensional and the second is two-dimensional. So one-dimensional is called as axis and the two-dimensional is called as meridian. Okay. Similarly, if you are able to define an imaginary line through the magnetic north and the magnetic south, you call it as You give a name to it. You call it as magnetic axis. Similarly, if you are able to define a plane, you call it as magnetic meridian. So these two are the important terms that we need to understand. Okay. So please make a note of these two on your books. Is it clear to this point? Yes. Yes or no? Right. So the first important point that is to be noted is the geographic axis and the magnetic axis do not coincide always. By now you would have got an explanation to it. Because I told you the direction of magnetic field at different locations is different. Right? So what is going to happen is the geographic axis and the magnetic axis will not coincide always. There will be a slight variation that is occurring between them. Okay, which is called as one of the components of Earth's magnetic field. First, let me read this out. So near the surface of Earth, the magnetic field of planet can be resolved into different directions. So near the surface of Earth, what can happen is the magnetic field due to the Earth can be resolved. Resolved means you can break it into rectangular components in different directions. And these components are the ones which are responsible for whom the direction and magnitude of the field at that particular point. Okay. So for which you need to know three terms. What are the three terms? One is called as magnetic declination. Okay, which is in simple language called as magnetic variation. Variation is not used in your book, but you can say magnetic declination is magnetic variation also. Is that clear? Okay. So this is the word that is used in your textbook. You can just write or variation and have it. Okay. First write down that word. Magnetic declination or variation.
Sir, we should write the above para also.
No, that's not needed. You just write down the heading as components of Earth's magnetic field, and under that first point is magnetic declination or variation.
Okay, sir.
Okay. So, what is magnetic declination? First, let's try to understand. It is the angle, write it down. It is the angle between the geographic axis and the magnetic axis. It is the angle between the geographic axis and the magnetic axis. Okay. So some books give it as it is the angle between geographic meridian and the magnetic meridian. So if I have to show you something, right? See, suppose you call this as the meridian. Okay, let's say this is the geographic meridian and this is the magnetic meridian. Okay, then the geographic axis will be somewhat perpendicular to this. Not somewhat, it is exactly perpendicular to this. And magnetic axis will be perpendicular to this. So how I define it as? It is the angle between the geographic axis and the magnetic axis. That is one way of defining. Or if you know the geographic meridian and magnetic meridian, if I hold the book like this, are you able to see the angle between them? Now they are perpendicular. If I make it like this, there is some angle existing. In that V shape, there is an angle, right? That angle is what is called as, so I repeat it. So this angle is what is called as magnetic declination or variation. Why we call it as variation is because it is something like a zero error that is occurring at a particular position. If you know the magnetic variation that is existing at a particular place, then it will become like a, say for example, if you have a weighing scale, okay. Let's say when nothing is kept on it, let's say it is showing -2 kilogram. And when you kept something on top of it, it is showing you 5 kilogram. What is the exact weight? That. So how did you get it? So it is because of the negative error that is there. It's the same negative error. Now what will happen is if the magnetic variation, for example, at a particular location is 18 degrees, and you want to reach a position which is exactly at 90 degrees, then you need to make the correction to go in a particular direction. Okay, I'll solve problems based on it. So that is why the most common term is variation point. Are you able to understand what I'm trying to say? The next is you have something called as angle of dip, or the angle of dip is also called as magnetic inclination. So one is called declination and the second is called inclination. So why we call it as inclination is, I'm not sure if you have seen this. When you take a compass, right? So generally the needle, it doesn't revolve this constantly. It is not stable. It will actually go like this. Have you ever observed it? So where is the needle pivoted? It is exactly at the center, right? So generally, whenever you face any object, when you hold any object at the center of gravity, it should not revolve around it. But you can hold anywhere. See, suppose I hold the pencil here, it is revolving, no? So this is not the center of gravity. If I hold it here, it is revolving. So if you hold anything exactly at the center of gravity, right, it should not revolve at all. But what is happening due to the Earth's magnetic field? So instead of revolving like this and showing us the exact direction, it is also getting dipped like this. So if I take this as the horizontal, I'm not sure. Guys, you are able to see? So if I take this as the horizontal, the magnetic needle will start dipping and revolving like this. So with respect to the horizontal, how much angle it is making with respect to, so okay, whatever is the angle made by the Earth's magnetic field with respect to the horizontal is called as angle of dip or angle of inclination. Are you able to visualize what I'm trying to say? So it is getting dipped, no? Generally, when you take the compass, right? So compass needle has a north pole and a south pole. So what is the direction of magnetic field? Away from the north pole, correct? So that is the direction of Earth's magnetic field. So if this compass needle, let's say this is the north pole, this is the south pole. When it is getting dipped like this with respect to the horizontal, can I say this is the direction of magnetic field? This is not the direction of this north pole, guys. This is the direction of magnetic field away from it. So the Earth's magnetic field is making an angle with respect to the horizontal. So the angle made by the Earth's magnetic field with respect to the horizontal is what we call it as angle of dip or magnetic inclination. Okay, please write it down. So right now the next heading is angle of dip or magnetic inclination. So what is it? It is the angle made by the Earth's magnetic field with the horizontal. Is that clear? The angle made by the Earth's magnetic field with the horizontal. And C. Just a minute. Listen. So if there is a direction of Earth's magnetic field, which I'll call it as BE, then this angle I'll call it as delta, where the delta is called as okay. Now this BE, can I resolve it into two components? Where I'll call this as BE cos delta and I'll call this as BE sin delta. This BE cos delta is what is called as the horizontal component of Earth's magnetic field, and BE sin delta is called as the vertical component of Earth's magnetic field. So the third type of Earth's magnetic element that we are going to discuss is horizontal component of Earth's magnetic field. So for you to define the horizontal component of Earth's magnetic field, what are the two important parameters that you need? Look at the mathematical expression. You need BE. What is BE? Earth's magnetic field, and you need delta. That is angle of dip. So when you have these two parameters, you can try defining the horizontal component of Earth's magnetic field, and it has an importance because the horizontal is the one which is making the angle with the Earth's magnetic field. That is why we don't consider about vertical component. If you know the horizontal component, then it indirectly tells you that you know the Earth's magnetic field and the angle of it. Okay, that is why the third component of Earth's magnetic field is horizontal component of Earth's magnetic field. Guys, does it make sense? Are you able to understand what I'm trying to say? Right. So one last point here. If I resolve it into two components, then what can I call tan delta as? Tan delta, I can write it as sine delta divided by, I'll multiply BE and DE here. I'll multiply and divide with it. What is BE sine delta? Vertical by horizontal. So sometimes in problems, what they do is they'll give you the vertical component of Earth's magnetic field and horizontal component, and they'll ask you the angle of dip. Then what are you supposed to do? Tan delta, you find it out by the formula BV divided by BH. Can you do that? Are you able to understand? Similarly, the last point is, what is the relation between BE and BV and BH? BE, can I write it as root of BH square plus BV square? Can I do that? Because what shape does it take? It takes the shape of a rectangle. So it's parallelogram law. Root of A square plus B square plus 2AB cos 90. So horizontal square plus vertical square. BH is horizontal. Horizontal component. BV is vertical component of whom? Of Earth's magnetic field. Is it clear? So with this, we are done with the chapter, but I told you about the problem, right, that I'll do tomorrow. So tomorrow we'll do 2-3 problems, after which we can proceed to the next step. Is it clear? So this is all this. That's all for today. Can you check out the first Guys, that's it from my side. We can wind up, okay? Those who are online, we can wind up.
Thank you, sir.